Hello, everybody. Welcome to Chloethedev Unfiltered. This is going to be another paper review. We are going to be going through combining Ghost and Casper. The authors labeled here. I guess I should. Yes, because my mouse doesn't show up, I'm going to. Let's see. Nope, that's not going to be fun. I'm not using GitHub Desktop. But if I download the paper, I should be hopefully able to put my cursor over the PDF. And it will not be in browser, but I can open it up. Okay, so let's see. Sorry. Is this it? Yes, this is it. So, as we go through this paper, let's save this. So, I have an hour till Bianca gets home. I'm going to try and get through this as quickly as possible. And so we're just going to get through it. I do stop a lot when I go through papers. This is for me, so I can keep track of what the papers I go through, keep track of my notes on the papers. And yeah, so if you want to follow along, feel free. You're always welcome, Casper. I had a video call. I was trying to test it out on this the new setup, so some things are moved around, but that's all right. And the still awaiting activation on the rocket pool nodes. So let's get going. I'm going to full screen this. That is not full screen. It does not. I've never used this before. Hide sidebar. Perfect. Okay. Vitalik Buterin, Diego Hernandez, Thor Kampfner, Kim Pham, Yi Kiao, Danny Ryan, Johook Sin, Ying Wang, and Yan Xiang. If I butchered any of those names, I am sorry, but I tried. October 31st, so pretty much last year this paper came out, and from what I understand, this is pretty much the implementation that is used for ETH 2.0 and like the way things are going moving forward. We present GASPER, a formal proof-of-stake based consensus protocol, which is an idealized version of the proposed Ethereum 2.0 beacon chain. The protocol combines Casper FFG, which is a paper I reviewed, I think last week on this channel, a finality tool, with LMD Ghost, a fork choice rule. We prove plausible liveliness, probabilistic liveliness under suitable synchrony assumptions, and safety under both static and dynamic validator set assumptions. So the paper is going to have introductions, setup and goals, main ingredients, main protocol, which is going to be GASPER. Talks about safety, which is going to go into plausible liveliness, probabilistic liveliness, and then in practice versus theory, and then the conclusion, and the conclusion. I will go into, I probably won't go into the appendix, but I'll do that personally if I, have fun. I might go into it here. I usually get sidetracked and just start digging into stuff, but we'll see. Introduction. Our goal is to create a consensus protocol for a proof-of-stake blockchain. This paper is motivated by the need to construct Ethereum's beacon chain in its sharding design. However, the construction is general enough that it could be used to, for example, design a sole blockchain and some brand new protocol with no sharding involved. So I think this is pretty cool because, again, papers like this are not just for Ethereum 2.0, but they're for the general good and they're public. You can just come read them at whenever you want. And you could just come use this to make your own blockchain, to make your own execution environment on Ethereum 2 or whatever you want. So this is kind of cool stuff. The consensus protocol presented in this paper combines the Casper FFG, their friendly finality gadget, finalization rule, and the latest message-driven LMD, greediest, heaviest observed subtree, Ghost, fork choice rule. Casper FFG is a finality gadget, which is an algorithm that marks certain blocks in a blockchain as finalized, so that participants can have full confidence that the block is considered to be part of the chain's history. So the whole point of blockchains is to figure out what is final, like what information cannot be changed, and that is what these different consensus algorithms are used for. It is designed to work on top of either proof of work or proof of stake chains. LMD Ghost is a fork choice rule where validators, which are participants in a network, so if you're having 32 ETH, you're going to be a validator, which is going to attest, which is going to vote on different blocks to see what's true. You attest the different blocks to signal support for those blocks. So you vote on a block showing support that this state is what actually happened. An idea which is similar to voting. Our protocol combines the two ideas for a full proof of stake blockchain, where time is split into epochs. So epochs are just periods of time that create checkpoints at epoch boundary blocks. So at epoch boundary blocks, you have different epochs, right? So these would be epoch boundary blocks. The space between it would be an epoch, which is a period of time. And participants build new blocks and attest to blocks with LMD Ghost on top of finalized blocks. So you build new blocks and attest to blocks with LMD Ghost on top of finalized blocks. Whew, very fun, very fun. In sections 2 and 3, we define our primitives, provide background knowledge, and state our goals. In section 4, we give our main protocol GASPER, which is a mix of Ghost and Casper. In section 5, 6, and 7, we formally prove GASPER's desired qualities. So again, like in all these papers, what I love about them is that they set up what we're talking about, then they show, what's the problem, this is our solution to the problem, and they're going to prove why this solution works. In section 8, we summarize some differences between GASPER and the actual Ethereum specifications, such as delays in accepting attestations, delaying finalization, and dynamic validator sets. We conclude with some thoughts and ideas for future research in section 9. So this is going to show at the end of the paper the difference between what GASPER is as a specification and what Ethereum uses in its own implementation. Because remember, GASPER, this paper, is a general specification that we use in any blockchain or to create any blockchain. Setup and goals. The main goal of this paper is to describe and prove properties of a proof-of-stake blockchain with certain safety and liveness claims. In this section, we give some general background on consensus protocols and blockchain. As the literature uses a diverse lexicon, the primary purpose of this section are to clearly pick out a specific set of vocabulary to be used for the rest of this paper. Again, really cool because they're going to teach us now the definition set for this paper's world. I like using the term of like each paper has set up its own little world, and in this little virtual world you need a set of rules to follow, and they're going to show us the rules that we're using. So consensus protocols, validators, and blockchain. Our goal is to create a consensus protocol, or a protocol for short form that from this point on. So every time we're talking about protocol, we're talking about consensus protocols, a protocol to attain consensus, which is agreement. Which is an agreed suite of algorithms or for a set of entities, nodes, people, etc., to follow in order to obtain a consensus history of their state, even if the network is unreliable and or if many validators are malicious. So even if all these other people are doing this random stuff, I should be able to know what the state of the network is. So I should be able to know what my balance is, or who sent what transfers to who, all this type of stuff on Ethereum. I should be able to know that in all of these parameters. We call the entities, people, programs, etc., who participate in a protocol validators, in protocol validators, denoted by a set, this wonderful little V. What was it, a promo, math calc in Markdown or whatever. They are called validators because of their data validation role in the Ethereum 2.0 beacon chain. Though the specifics of this role are not part of our abstract protocol. Other works use many different words for the same concept, e.g. replicas in classic FBFT literature, block producers in DPoS and EOS, peers on Peercoin and NXT, or bakers on Tezos. I don't like any of these. I don't mind block producers in the DPoS system, because in the DPoS system you are producing blocks. I guess Peercoin, you're actually peering. Baking for Tezos confuses me. I'm not gonna lie. I like just calling them validators. I like that. I like how Ethereum just tries to be this base general layer for everything just to work on. I enjoy that a lot profusely. The validators are connected to each other on a peer-to-peer network, which means they can broadcast messages, typically packet the data to each other. In the types of protocols we are interested in, the primary types of messages can be interpreted as proposing pieces of data called blocks. The first block is called the genesis block and acts as the initial blank slate state. So it's just empty. It doesn't mean anything. We're starting from here. Other blocks are descriptions of state transitions with a pointer to a parent block. So again, you're going to have this starting state, and then every block after it so the next block is going to point to the genesis block with changes to genesis block state, and that's what the next block contains. And the third block is going to point to the second block, which is the parent block of that block, and the parent block of the child block with the third block, and the fourth block of the child block, and the fifth. It continues to go with changes of state to the previous block. A block is just an instantiation. For example, with specific network condition, validators, whatever, of such a consensus protocol, where we use blocks to build the overall state. We do not want all blocks in the network to be accepted as common history, because blocks can conflict with each other. So if you have multiple blocks all saying they're a second block, how do you know which one actually is the second block? You need validators to attest, to vote, to pick them. These conflicts can happen for honest reasons, such as network latency, or for malicious reasons, such as Byzantine validators wanting to double spend money. So basically just saying, for example, maybe if your network has issues, you're offline, you didn't get to vote. So that would be an issue of where you're not getting a live vote, right? Or if a whole part of the country has a blackout, would be an example where you might get 2/3 of the network offline off of some sort of system that does not have to do with a malicious actor. In Toronto, though, it's happened once where the entire city of Toronto just went out, and that could be pretty bad if electricity is cheap, which it's not cheap in Toronto, and everyone's well, I guess you don't need that anymore for validating. If everyone in Toronto is validating lots of ETH, that could be an issue. Graph theoretically, one can think of choice of history as a choice of a chain going from the genesis block to a particular block. Thus, a consensus history is a consensus of which chain of blocks to accept as correct. This is why we call such an instantiation of our protocol as a blockchain. So that's all a blockchain is. A blockchain is a chain of blocks, which is telling you the state that we're starting at, the state we're currently at, and then what chain of blocks to go through to get all the state conditions to get there. That's literally all a blockchain is. Example 2.1. Assume a goal of a protocol is to keep a ledger of every validator's account balances. Then their collective state is the ledger, and each block captures a state transition. Such a monetary transition from one validator to another, for example, Eunice sends coins with ID 538 to Bernard. One type of conflict we may want to avoid is having both the aforementioned transaction and another transaction with contact Eunice sends coin with ID 538 to Carl be accepted into consensus history, an act commonly called double spending. So Eunice is trying to send coins with the same ID to two different people, Berard and Carol. The current consensus state can be determined by starting from a genesis state and sequentially processing each message in the consensus history. Hopefully, one that all honest validators agree with, starting from the genesis block. Sorry, all this talking gets me dehydrated. 2.2, messages and views. In our model, a validator V interacts with the network by broadcasting messages which are strings in some language. When an honest validator V broadcasts a message M, we assume M is sent to all validators in the network. The main type of message proposes a block, which is a piece of data, to the network. Other messages can be bookkeeping notices, such as voting for blocks, which is attestation, putting new validators on the blockchain, which is activation, proving bad actors of other validators, slashing. Proving bad actions of other validators, slashing, or etc. So there's other things that a validator can do, but the main type of messages is attestations. So the main type of message is the block is proposing a block, which is a piece of data to the network, and then everything else happens on top of that. We assume that each message is digitally signed by a single validator. We can go through this. So here, when an honest validator V broadcasts message M, we assume M is sent to all the validators on the network. Oh no, what happened? The model of the validators, we model validators as sending a single message to an abstract network which handles the message. In practice, it may be part of the protocol that, for example, every honest validator rebroadcasts all messages that they see for robustness. We consider these implementation details not important. So yeah, implementation details, specifics that are not important. And other blocks are descriptions of state transitions with a pointer to a parent block. Our choice that each block has a unique parent is almost taken for granted in blockchains. One can imagine blockchains where blocks do not need to have parents or can have more than one parent. See, for instance, hash graph. Even the very general structure of block itself may be limiting. Very interesting. I'm not going to go there right now, but if you'd like to go there, look at hash graph. That sounds complicated. I know a hash graph, but like I'm saying, to try and make a blockchain out of something like that sounds complicated. Which means we can accurately trace the author of each message and attack, such as impersonation and of honest. Okay, where were we? We assume that, so because each message is digitally signed by a single validator, it's like because you sign your check at the bank with your signature, it means you can accurately trace the author of each message, the signer of each check, and attacks, such as impersonation of honest validators are not possible. So basically, because you're signing all your checks, all your messages with your signature, digital signature, it's impossible for someone to impersonate you, or sign twice or whatever. Well, without being caught, hopefully. Due to network latency and dishonest validators, delaying messages or relaying incorrect information. Validators may have different states of knowledge of the full set of messages given to the network. We formalize this by saying that a validator either sees or does not see each message given to the network at any given time. Oh, why is my picture so small? That is hilarious. So sorry, that was really funny. Where'd the paper go? So yeah, basically just saying everyone from anywhere can send messages or attest to things or send messages, but not every validator sees every other message. So basically, at any given time, each validator's state can be a little bit different. What they see is a little bit different. Each message may have one or more dependencies, where each dependency is another message. At any time, we accept a message if and only if all of the dependencies, possibly none, are accepted, defined recursively. We now define the view of a validator at a given time t, denoted as view of a validator at a given time. See how that's simple? View of a validator at a time. As a set of all the accepted messages the validator has seen so far. So if you want to know all the messages a validator has seen so far, you go to a certain validator at a certain time, and you you check the view right here. We also have a God's eye view that we call the network view. So this is not what the validator sees. This is what the network sees. Defined to be the set of accepted messages for a hypothetical validator that has seen with no latency, which again, impossible, all messages any validator has broadcast at any time. This includes messages sent by a malicious validator only to a subset of the network. So again, unrealistic, obviously, more of a theoretical God's eye view. We will treat the network as a virtual validator. So we use the view of this, what do they call it? Yeah, I don't know why virtual validator, but the network view. Anyways, the point is view of the network at a certain time. To denote the network view at a time t. For any validator v and any given time t, view of network view at a certain time includes all of the messages in the view of the validator at a certain time, though the timestamps may be mismatched. I guess because this God's eye view has the real time, and then the validator view might have a delay, and so that time might be wrong. Wrong, right? God is always, God will be right in this scenario. Example 2.2. At time t, suppose validator v sees that message m with content Eunice sends coin number 5340 to Bob, but has not yet seen message m prime containing Eunice obtains coin number 5340, which is on the network but has not yet made its way to the validator. So basically, a validator sees a certain message, right? But has not yet seen a second message that's out there. Also, suppose that in our protocol, this message depends on this second message. So there's the first message depends on the second message, and no other message, which captures the semantic meaning that we need to obtain a coin before spending it. So, for example, the network, there's two messages in the network. One message saying, I'm going to spend a coin. Another message saying, I'm receiving the coin. But the validator hasn't seen the receiving coin and has only seen the spending coin. How do we deal with that? And that the validator cannot and should not act on the first message without seeing the second message, right? So here's an issue now. What do you do if the validator is like, hey, vote on this information, but we only give you half the information? You can't vote. What do you do? In this situation, we say that the validator has seen but not accepted this first message. So the message is not in the view of the validator at that specific time. However, the network has seen both. So if the validator accepts that second if the network accepts the second message, right, which should be true, we have the message is within the view of the God's eye view, which obviously, let me get some more water. Which makes sense, right? Because the network is only going to accept the message if more than 2/3 of the validators have accepted it, which means that other validators have seen both, so the network has obviously seen both, right? Because other validators in the network have seen both, so it's included. So you got to make some assumptions on the structure of views. Everyone, the validators in the network, structured with a single message with no signature corresponding to a single agreed upon Genesis block denoted to be Genesis, so block for Genesis with no dependencies. So it starts out automatically accepted into all views. So all validators looking at the same state at the beginning. Each block besides B Genesis refers to and depends on a parent block. So B Genesis is the only block that has no parent block. It is the parent block. Thus, we can visualize view of a validator, which is the V, as a directed acyclic graph. In fact, a directed tree. Okay, so basically, it's a directed, so there's a direction. Acyclic, there's no cycle, so it's a tree, and it goes in a certain direction. Rooted, so the start of this tree, the root of this tree, is the genesis block, with an edge of block of B prime, so B the second block. If the block is the parent of this B prime, with the child block, the block that's included off of it. In which case, we say that B prime is a child of B, this the first parent block. We call these parent-child edges to differentiate from other types of edges. My stomach is really hurting. Gosh. We're going to keep going, though. Only 5 pages in. A chain in the protocol would then be a sequence of pairwise parent-child edges. So you have the block 1, you have block 2, and so on. If there is a chain from B to B prime, we say that B prime is a descendant of B. We say that B is an ancestor of B prime if and only if B prime is a descendant of B. We say that 2 blocks, B and B prime, conflict if they do not equal and neither is a descendant of each other. So for example, what we're saying is B, if you have any B and you have any B prime must be a descendant of B. B must be an ancestor of B prime, or else this must. If not, something's wrong. It can't happen. It conflicts, man. It conflicts. Something's wrong. Someone needs to get slashed. You're voting on the wrong information. It shouldn't happen. The above setup implies each block B uniquely defines a backwards chain starting from B genesis to B. And this must be the same chain in any view that includes B. Thus, we do not need to include a view as part of its definition. We call this the chain of B, or chain B. So B genesis has all these blocks. So here, we're going to look at figure 1, which is going to be a graph, which is a visualization of a view. So this is a view of B, but again, they're taking out the name. Only visualizing blocks and not other messages that occurs in the types of protocols. A graph visualization of a view that occurs in the types of protocols we care about. Okay, so this is will be a block, right? Where you get to B. Although I think they're just going A, B, C, D, E, and not even using B here. But anyways, you have B genesis, you come here, you go through here, and this would be the longest chain. I wish they went into more. I dislike when you use a beautiful diagram, and then oh, it's here. This is why it's called Chloethedev Unfiltered, because I ain't going to cut that out. See figure 1, for example, of a view. Arrows portray parent-child edges. Views look like trees rooted at a single genesis block, B genesis, yep. Here, blocks C and D conflict. Yes, we know this because they're the same block. Again, they're using the same letter, like B here, so I guess numbers might have been, I don't know, better ways. I don't know. It's not a big deal. It's a pretty simple topic, I suppose. C and D conflict as well as E and D. Get it? Because you can't have, arguably, this would be the heaviest chain, and I suppose this would win. But, yeah, E has the longest chain, which is then chain E. So it would be chain E, right? So this is the blockchain we're talking about now. So chain E is the blockchain that gives you E, where you are, back to the root chain genesis. So, or other way around, I guess, from root to leaf. So chain E would be B genesis, A, B, C, D. Arguably, if you wanted the chain for D, then you go B genesis to D. But that would be like if you wanted to talk about the two chains, like C, the chain C and chain D, to talk about how these two chains are conflicting, then you could talk about it that way. Chain C is B genesis A, B, C. Chain D is B genesis A, B, D. Anyways, there are some technicalities to our wording in this section that motivates our definitions of views, but are not very important to the core of this paper. To not distract the reader, you defer these details to Appendix A. And this is why I was saying I don't want to go through the appendix in this live stream, but I'll probably go through it. So now we're going to define proof of stake. The first and most influential approach to blockchain protocols is Bitcoin, using a proof of work model. This approach makes it computationally difficult to propose blocks. Using the simple and intuitive fork choice rule, the block with the heaviest chain is the head of the chain. Miners, with the analogy of validators, simply propose blocks to build on the heaviest chain, the chain with the most amount of computational work, which does not mathematically guarantee any non-genesis block as correct, but offers a probabilistic guarantee since it becomes less and less likely to conflict with a block once other miners build on top of it. Then, the consensus history is simply the chain with the heaviest amount of work, which ideally keeps growing. The elegance of proof of work is paid for by the expensive cost of computational work, electricity, etc. It costs a lot of money to run these computers, therefore that is the cost of securing the network. In this paper, we want to create a proof of stake blockchain, where a validator's voting power is proportional to their bonded stake or money in the system. So stake is just your funds, your money, your finances in a system. Instead of using computational power to propose blocks, proposing blocks is essentially free. In exchange, we need an additional layer of mathematical theory. And I love it because instead of using just what we have, we're trying to create some, mathematical, magic. You can call it magic, call it theory, call it whatever you want, to try and secure these assets instead of using, actual goods. And I think that's a beautiful thing because when you use electricity, it has to be used up. It has to be burned up. All these things have to be used and extracted. Where if we're just using assets and math and theory, then arguably, potentially we can use that same Bitcoin hash power maybe for something more valuable. Maybe for something like, curing cancer or something like that. Let's use hash power to cure cancer, and let's use mathematical theory to secure our assets. That's kind of how I see this. So that's to prevent perverse incentives that arise when making proposing blocks easy. We now shift our paper's focus to a family of blockchain designs with proof of stake in mind. To start, we assume we have a set of n validators, V equals, V1 to V of n, and that each validator, V, is a set of, validators. Each validator, V is a set of validators, has an amount of stake, a stake weight, I'm assuming that what W is, right, for the validator, which is a positive real number describing an amount of collateral, so an amount of your stake. We make the further assumption that the average amount of stake for each validator is 1 unit. So the sum of the total stake is n. All of our operations involving stake will be linear. So this scaling does not change in the situation and makes the bookkeeping easier. We assume validator sets and stake sizes are fixed for the sake of focusing on the theoretical essentials of the protocol. We address issues that occur when we relax these conditions in the practical use when we relax these conditions in practical use in later sections, especially in section 8. The main ingredients we need are a fork choice rule, a function fork that, when given a view G, identifies a single leaf block, a vertex with no descendants. B. This choice produces a unique chain, fork G equals chain B from Genesis to B, called the canonical chain. The block B is called the head of the chain in view G. Intuitively, a fork choice rule gives a validator a law to follow to decide what the right block would be. For example, the longest chain rule is a fork choice rule that returns the leaf block, which is the farthest from the Genesis block. This rule is similar to the heaviest chain rule used by Bitcoin. So you need a fork choice rule, which up here would be an example where here it would return the longest farthest chain from B Genesis, which would return the chain of E, BA, BC, BCE. You need a concept of finality. So that's how you choose which blocks are in the blockchain, but that doesn't give you any finality. Finality is a deterministic function f when given a view G, so you give it a certain a block. So we would say we're going from E here. So you give it a view, right? And it returns a set of finalized blocks. So maybe the set of finalized blocks won't go all the way to here, but maybe you say, you know what, 2 blocks past this block, the longest block, is going to be finalized. So B would be finalized. And then once you have, let's say A, B, C, D, E, you have F over here, maybe then C would be finalized. And then once you have G down here, E would be finalized. So maybe you'd follow by two blocks behind, for example. Intuitively, finalized blocks are blocks that everyone will eventually think of as part of the consensus history or what the blockchain is sure of. Then you need slashing conditions to get back on those bad people, those malicious actors, or sometimes, people that just make mistakes, but still, you need to penalize bad people, bad nodes. The key concept we use to define these ingredients are slashing conditions. These are conditions that honest validators would never violate, and violating validators can be provably caught, with the idea that a validator's stake would be slashed or destroyed. So slashing means your money, your stake, that an economic incentive that you put into the network and put in to provide security, it gets cut away, taken, removed. You do not have it anymore. Slashing conditions incentivize validators to follow the protocol. The protocol can reward honest validators for catching dishonest validators violating the conditions, for example. So I think this is, just like how regular society works. If you can get away with something, then you can get away with it. But you have a set of rules, and everyone has to follow these rules in order to be part of the system. And if you try and break these rules, you vote on something you're not supposed to, or you just break the rules set, then you will have a set of conditions that will penalize you in a way that should hurt your viability of the network. So eventually, your slashing should remove you from the network completely, removing your entire stake, and completely remove any ability you have to continue attacking the network. The key concept we use to define these ingredients are attestations, which are votes embedded in messages for which blocks should be the head of the chain used. So basically you're voting on which blocks should be the head of the chain using the fork choice rule backed up by depositing stake. To prevent validators from double voting or voting in protocol breaking ways, we enforce slashing conditions for these rules, which can be used to destroy a validator's stake, incentivizing validators to follow the protocol. One can see an idealized version of the protocol we will present in Figure 2. In Section 4, we will define all of the details. So, I'm guessing this is this Figure 2 we're going through, so I'm getting really tired now. So I'm drinking some water. I think it's just the weather is starting to get me tired, but that's all right. So you have the Genesis block, which is the root. You have, these are the blocks. These are the attestations over here. These circles, people are attesting to blocks, saying, these blocks are correct, these blocks are not. So B depends on A, which makes sense because let's say you have an empty state and then you have a bunch of changes to that state, which is what's going to cause block A. And you have all these little circle things attesting to what's happening on block A. Then you have to have block B, which relies on that state from block A. Without block A, what would you be changing the state of? So like, for example, say you had $10 here and you sent it to Susie, and then Susie got it here. You're changing the state from 10 to 0 for yourself, from A to B, and then Susie would go from 0 here to 10 here. You're changing the state from the previous block. And then also B Genesis, and then some certain amount of blocks, then to A, B, C, is basically saying that this is the chain of C. This is how we got from this root chain that we started at all the way to C. An ideal situation where in each slot a new block is created with the parent block being the last block created. And validators in the corresponding community all perfectly attest to the new block. In less idealized situations, the blocks may fork. We may have missing attestations and so on. So this is the ideal situation here. And above, we saw a situation where, you might have forks, you might have differential situations where, you're going to have to choose between these things. Okay, after this chapter, I'm going to take a little break. I am really hungry and really tired. Oh, man. Byzantine validators B, I always say B first, PBFT. In a protocol, we call a validator honest if he or she follows the protocol and Byzantine otherwise. So if you're not following the protocol, you're Byzantine. We typically assume strictly less than P equals 1/3 of the validators are Byzantine. So basically you're assuming less than 1/3 of the total active validators are malicious. This constant can be traced to practical Byzantine fault tolerance, which is the PBFT that I keep saying the B first in. A classical consensus protocol in Byzantine tolerance literature. PBFT ensures that the system runs correctly as long as less than 1/3 of the replicas, validators, are Byzantine, as proven in another paper. This constant 1/3 tolerance appears frequently in many works based on PBFT. The main idea is that a pigeonhole principle argument needs the 1/3 to work, such as in our proof in section 5. So we'll see the proof, don't you worry. With Casper FFG being the most directly relevant to our work, we will show details of Casper FFG in section 3.1. One of the most important aspects of PBFT is that it works under asynchronous conditions. This means we have no bounds on how long it may take for messages to be received. Very important because you don't know when people may be offline, online, whatever. Thus, it is robust to the demands of blockchain cryptocurrencies, where we often worry about adversarial contexts. We will discuss synchronicity assumptions further in section 2.6. Very cool. 2.5, safety and liveliness. The ultimate goal for the honest validators is to grow a finalized chain where all blocks form logically consistent state transitions with each other, despite having validators potentially go offline, suffer latency problems, or maliciously propose conflicting state changes. Formally, This translates to two desired properties. Definition 2.4, we say a consensus protocol has safety if the set of a finalized blocks, so you have a finalized set of finalized blocks here for any view of G, can never contain two conflicting blocks. Okay, so that's what safety means. So, for example, when Madasha, the testnet running on Ethereum 2.0 currently, it's actually safe right now, but it's not finalizing, I think, currently, last I checked. And all that really means is you're still proposing blocks. Blocks are still coming out. Blocks are still happening. But you cannot be sure, 100% certain, that these blocks will not be changed. So you do not have that safety. And I think it's such a great word to use because that, in my opinion, is the definition of having is safety in blockchains. I feel safe using Ethereum the more blocks are mined, but in this new definition of safety, it's not based on all these new blocks. It's just when this block is final, it is final. And that's what we're supposed to be having with this definition. A consequence of having safety is that any validator view, is finalized blocks. So the finalized blocks in this validator's view can be completed into a unique subchain of the finalized blocks for the network view that starts at the genesis block and ends at the last finalized block, which we call the finalized chain. So it's a positive consequence is that now any validator, right, can take their view of the network and then look at the total network view and find their view within that. And that should give you this finalized chain that we're talking about. And then liveliness is what we had with Madasha, even though we didn't have finality. And what we have now on Madasha is, you know what, I'm going to try and pull it up. Or I'm at least going to see. Because if someone comes to this, they might see this. Okay. So I am going to show this because I think this is a pretty cool way to see it. Oops, that's not what I wanted to show. This is what I wanted to show. So as you can see, this is Madasha right now on Beacon Chain. It's a website showing, it's like Etherscan. It shows a bunch of information about the Madasha. So right now there's only 90% network participation currently. I'm getting my rocket pool node set up, and so right now a bunch of validators are gonna get slashed, and eventually the network is gonna pick back up with the networks with the nodes that are allowed to run. So I have 3 rocket pool nodes above that are awaiting activation on Madasha, and hopefully they will soon be included in this. But the network is still live. So if you look, you can see 6 minutes ago, there was an epoch of blocks. This epoch was not finalized or has not been finalized. 60 minutes ago, this epoch, there was 8 million ETH eligible. But as you can see, the ETH amount that is staked is dropping steadily. This is ETH that is being slashed, that is being inactivity leak, that is being leaked out of the system. So it's very interesting to see it happen in real time and be able to watch all this stuff happen. But yeah, you could see the active validators. I mean, this looks really weird how it's saying 0 active validators. Maybe the whole network is just not working. But either way, you could see, I mean, there's voting happening. So I think there's some active validators somewhere. I don't know. Either way, you can see the ETH that is coming down. And you can see the most recent blocks, the block proposer, 8 days ago, though. And that's when Zinkin came out and other networks came out. So maybe since then, they're not looking at it as much. But still, now you can see it's at 38%. And then it keeps resetting. So you can look at this to try to understand some of this information in real time. Let's close that. Let's go back to the paper. Where are we? There we go. So we have liveliness, like I said. If the set of finalized blocks can actually grow. There are different ways to define liveliness. In our paper, we say the protocol has plausible liveliness if, regardless of any previous events, attacks, latency, etc., it is always possible for new blocks to be finalized. Alternatively, it is impossible to become deadlocked. This is to prevent situations where honest validators cannot continue unless someone forfeits their own stake. If regardless of any previous events, it is always possible for new blocks to be finalized. That's not what I see in Ethereum, but okay. Then you have probabilistic liveliness. If regards to any previous events, it is probable for new blocks to be finalized. I think that's what we got on Ethereum, because it's probable that if someone attacks the network or nodes come offline, eventually, after a long enough inactivity leak, that blocks would start getting finalized again. So once we make some probabilistic assumptions about the network latency, capabilities of attackers, and so on. On first glance, the latter implies the former, but the situation is more subtle. The former is a purely non-probabilistic property about the logic of a protocol. The latter requires potentially very strong assumptions about the context of the implementation to guarantee that the protocol usually works as intended. So yeah, these don't sound the same at all to me, but yes, this is a very good explanation of why they're not the same, and I guess we'll further discuss why in section 7.3. Our main goal in this paper is to prove these vital properties for our main protocol in section 4. Remark, syntax versus semantics. It should not be immediately obvious that chains have anything to do with logical consistence of state transitions, and this requires more work on the part of the protocol designer to ensure. For example, one can dictate a protocol where a block that allows a user to spend a coin S forbids an ancestor block from using S in another transaction. In this situation, if Xander obtained a coin S from block X, block X, and writes two blocks, block Y and block Z, such that block Y's data includes Xander paying S to Yeezus. Okay, I need a whiteboard for this when I start doing it, of these diagrams. And block Z's data includes Xander paying a double spend. Xander is trying to pay Yeezus and Zachariah S. Then the logical idea is that these actions are inconsistent correspondence to the graph theoretical property that block Y and block Z conflict as blocks. The language of chains and conflicting blocks is enough to serve any such logic. So we assume that in our paper that the syntax of what blocks can be children of what blocks has already been designed to embed the semantics of logical consistency, which allows us to ignore logic and only think in terms of chains and conflicting blocks. Very true. I mean, I guess helpful for writing the paper. There's explaining why they did it that way. 6.2, time, epochs, and synchrony. In our model, time progresses in slots. For example, imagine every slot is 6 seconds long. A collection of C slots is called an epoch, where C is a fixed global constant. the epoch j of slot I is the epoch of I, right? So that's a slot is the epoch I. The epoch of, sorry, oh my gosh, is the epoch of I slot equals j, sorry, the slot I over the constant is going to be your epoch. So you're going to have multiple blocks in each epoch. I always get confused when you call something a slot or an epoch, right? But a slot is a block. So you call them slots, call them blocks, call them whatever you want. But this whole new idea of slots is just a block, right? So now blocks are just slots of time, from what I understand. So a collection of C slots is called the epoch. Okay, so here you have your one slot, which is your one block, over your entire collection of slots, right? Which you're going to be in your entire, J is the entire epoch. So yeah, so if you're going into one epoch and you're trying to just find a certain block, you're going to go into that larger epoch, which we saw on the other website, how you had the epochs ticking up, and I was like, there's a bunch of blocks in each epoch. And I guess you're going to you'd write it out as like that. So, have the slot numbers J for the certain epoch you're using, and then the certain slot. I guess plus K, as K runs through 0 all the way to C to the -1. The Genesis has a slot number of 0, and is the first block of epoch 0. So, I mean, this seems like a very, complicated way of writing it out. I mean, obviously, once you get into the paper, like when you get into the math of it, I feel like this stuff makes more sense. But in simple terms, you just have blocks, which are now called slots. Each slot, let's say it's 6 seconds, they just continue going and going and going and going and going. But these slots are also grouped into epochs, which are periods of time. And that's just how you group slots together in epochs. That's all it's trying to say. The main purpose of epochs is to divide time into pieces, the boundaries between which can be thought of as checkpoints. It allows concepts for Casper FFG to be used, as well as we see in section 3.1. So from what I understand, the only reason you need that is so you can have some finality. You can, for example, say that, okay, all the blocks from 2 epochs away are finalized. We should not assume the network is guaranteed to have the same thing happen for everyone, or even that the different validators have the same view of time. The study of consensus protocols addresses this issue by having different synchrony conditions, such as a synchronous system has explicit upper bounds for time needed to send messages between nodes. An asynchronous system has no guarantees. Recall that PBFT works under asynchrony. A partial synchronous system can mean one of two things depending on context. From what I understand, Ethereum 2.0 is partially synchronous because if you don't attest within 32 blocks or 32 slots, you lose your reward. Explicit upper bounds for delays exist, but are not known a priori in advance. Explicit upper bounds are known to exist after a certain unknown time. The work establishes bounds on fault tolerance in different fault and synchrony models focusing on partial synchrony. To capture the notion of partial synchrony above, we say that the network is T synchronous at time T, where T and T are both units of slots. if all messages with timestamps at or before big T minus small t are in the views of all validators at time big T. For example, if each slot is 6 seconds, then partial synchrony means that all messages are received up to 3 seconds later. So, for Ethereum, if you want, you have to attest at certain blocks within a certain, attestation distance to be included. And I think that will be similar here. We will make this assumption when we look at probable liveliness and make no assumptions about synchrony otherwise unless explicitly stated. Remark, it is possible to, for example, receive messages from the future. Suppose Alexis sends a message timestamped at 1 minute and 30 past the hour, and Bob's receives it 1 second later with a clock that is 3 seconds behind. Bob sees the message at 1:30. Message on his own time stamped at 1:28. This is because he is a net total of 2 seconds behind. To make analysis easier, we can assume that all honest validators always delay the receiving of a message. Do not add it into their view until their own timestamps hit the message's timestamps. This allows us to assume no messages are read in earlier slots than they should. So this isn't really true, right? This isn't really going to happen. But by using timestamps and using this probability, they're trying to say that, for example, I guess if I am a validator signing an attestation that I'm seeing is coming before me, it's all right because they're going to assume I'm going to wait till it sees me anyways. So maybe I'm just going to take it and change the time to my current time, or if it's signed, maybe they're just going to assume that as long as it's close enough, I wouldn't sign anything too far out of bounds anyways. As long as it's close enough, I'll sign it, and the network's going to assume that I'm holding on to this message until if I get this message at 1:28, the network's assuming that I'm going to hold it till 1:30 regardless of what time I see this at. I'm going to hold it till my clock reaches the time. And then we're getting to chapter 3. I'm going to stop here. Bianca should be home in 5-10 minutes. I'm probably going to start, getting ready for her to get home. But hopefully, what page did I get to? Not very far in the paper, eh? Page 10 of 50. So we'll get to this soon. Yeah, I'm supposed to be doing more stuff, but we'll see where I get to. Hope everyone enjoyed the stream if you came in. And I hope you learned something new. The paper is linked, and I hope you enjoy reading it.